I will prove this one and then I will show you how this follows from this. Okay, so as usual we form the truth table. We have two statements x and y, two independent statements, and we have their disjunction, and since we have space we are going to include the final statement also. Implication, because you see in this case we have to carefully see what is the case, that is what happens to the hypothesis and what happens to the conclusion. What I am trying to say is that in our previous proofs of the other laws of logic, we had things like this, right? Something was logically equivalent to something. We did not need a column for this, separate column, because we could read off the entries on these two columns and see whether they match. In this case, that's not what we want. An implication does not demand that they have to be the same. Remember, implication is true if this is true and this is true, or this is false. Okay, so this case is separate from what we previously had. So let's draw the table. Two independent statements we have. So there will be 4 rows. And the columns, of course. Right. So we quickly write the possibilities: false, true, false, false. Now disjunction is true if either of the statements or both of them are true. So in the first 3 cases, the disjunction is true. Only in the last case, the disjunction is false. Okay, now you look at this. Now we are dealing with an implication where this is our hypothesis and this is our conclusion. So from a true hypothesis, we can only have a true hypothesis. I mean, we can have a false hypothesis, but then the implication will be false. Okay, recall carefully. When this is true, then the implication is true only when the conclusion is also true. If hypothesis is true and conclusion is false, then implication is false. In this case, you see, hypothesis is true, conclusion is true. So that means this is implication is true. True, true, true. However, for these 2 cases, you see the hypothesis is false. So the implication is vacuously true. So these 2 cases are vacuous truth. In any case, this implication is always true. So that means we have proved that this always holds, right? And that is the proof that this is a tautology. Now, how does this one follow from this? You see, suppose we are given this one and we want to prove this one. Okay. This may sound somewhat strange, but try to follow me. You think of y as x. These are just names given to some statements, right? We have some statement x that implies this. In place of x, you can put any statement, and that statement you can call y also. It's something like this. Suppose a is a real number and a happens to be equal to 1, and you decide to call it by another name, b. There is no problem with that. Here we had x, but x can be any statement. X can be y also. Not this y, of course, but any statement y. So in place of x, if we are putting y, what I am trying to say is that we can interchange x and y. For example, suppose x is the statement a is equal to 1 and y is the statement a square is equal to 1. Now, if you have something like this involving x and y, will the thing change if I call this one x, y and this one x? Nothing will change because the statements continue to be the same, only the names have changed. For example, if you have two persons, one is say Raj and another one is Jay. If you call Raj Jay and Jay Raj, have they changed as individuals? They have, of course, there will be a confusion, a whole lot of confusion. But if for some reason they had to swap their names, their identities won't change. Only the names have changed. Okay, they continue to be the same person that they were before the name change. So what I am saying here is that if I write y in place of x and x in place of y, nothing changes. The statement continues to be true. So y implies y or x.